Hello, today we have this chain streets problem. Essentially, we have an infinite binary tree. Every node of this tree has the probability p to be equal to 0, otherwise it's going to be equal to 1. And we have to find for what p the probability of an existence of a path with the sum of all nodes being either 0 or 1 to be 1/2. Now, I thought that the problem is a little too simple, so let's replace this 1 with n. Alright, now let's work on the simplest case, n is equal to 0. Well, if we're to look into the very base of it, obviously it has to be 0, so the probability for that is going to be p times something. What is it? Well, if we're to look into the children, they themselves are also infinite binary trees, and for them to have a 0 path is gonna be the same exact probability. So what we can do that is we're gonna name this probability a, and we're gonna say that this equals to p times a plus a minus a squared. Well, now we can divide everything by a, but first we have to know that a is not equal to 0. How do we know that? Well, if a was equal to 0, then this wouldn't make sense because it's supposed to work for every single p. However, if we were to choose p equals to 1, then every single time there's going to be a path. It's going to be all zeros. Alright, now 1 equals to p times 2 minus a, 2p minus pa equals 1. 2p minus 1 equals pa, and well, a equals to 2p over p, 2 minus 1 over p. Now we're just not going to pick p0, because if p is 0, then everything's going to be 1, and all paths are going to diverge, which is not something we're looking for. So I can seclude p equal to 0. Alright. Now that we have gotten this out of the way, let's define a function f of I, and the argument is going to be p. Well, fi, every fi is going to be basically this, however, instead of at most is precisely n. So I've already found for 0, f of 0, f0 of p is going to be 2 minus 1 over p. Now if we look into the latter examples, then let's take the path for 1, for example. Well, there are two cases how we can deal about that. Either the first node is 0, and then the children are supposed to have a path of 1, or the first node is 1, and the children are supposed to have a path of 0. So how do we generalize that? Well, we say fi of p is first case when we hit the p, so the base node is 0, then we have 2 fi p here minus fi p squared plus, now we review the case when it's not the case. Well, the path is going to be demanded in the similar manner, where instead of f of I is going to be fi minus 1 of p minus fi minus 1 of p squared. Alright. Good to go. Now let's swap some notation for simplicity's sake. Let's change fi minus 1 of p for b and fip for a temporarily for simplicity's sake, or rather, speak nicer letters, let's say we have alpha and beta. Right. P times 2 alpha minus alpha squared plus 1 minus p times 2 beta minus beta squared. Alright, now let's open this part. We have alpha squared, p alpha squared plus 1 minus 2p alpha plus, now we're passing this to the other side, so we have to negate it, p minus 1 times 2 beta minus beta squared is equal to 0. Now, if we were to look into this, we know that p lies between 0 and 1, so p minus 1 is guaranteed to be either equal to 0 or less than 0. It's going to be less than or equal to 0. And 2 beta minus beta squared is going to be greater than 0 on the interval from 0 to 1. How do we know that? Well, again, beta is bounded this way. Now we're to look into this parabola, beta squared minus beta squared plus 2 beta. Let's find the roots of it. Well, multiply this by -1. Next, let's add 1 to both sides. And you get beta minus 1 squared is equal to 1. And beta minus 1 is equal to plus minus 1. Beta is equal to 1 plus minus 1. Alright, so the roots are going to be 0 and 2. Now the parabola has branches going down, so it's going to be something like this. Alright, now that I have reviewed that part, we know that the coefficient c is negative, therefore one of the roots is going to be, well, negative. Then the other root is positive, and we're looking for the positive root, so we're looking for the greater root. So we're not going to review the minus part of the quadratic formula. Alright, now 2p minus 1, we have 2p here, alright, plus the square root 1 minus 2p squared is going to be 4p squared minus 4p plus 1 minus 4 p times p minus 1 times 2 beta minus beta squared now if we were to work with that expression, then it's fairly easy to factor it, except you still will have 1 left, so it's not proper factorization, but you get a decent chunk clumped together, and that's already nice. So you can bring out 4p here, then have 4p p minus 1 like this, so we can bring it here. What you have is 4p times p minus 1. Next we have 1 minus 2 beta plus beta squared plus 1. Now you can replace this with beta minus 1 squared. Alright, and now we can write it down nicely. Now that we have gotten the expression, fi of p is going to be 1 minus square root of 4 p minus 1. Next we're going to have fi minus 1 of p minus 1 squared plus 1. Alright, very nice. So how do we go about finding the at most part now? Because we have gotten the specific part, well, what we can do is we're gonna define q. Let's say the q of 0 of p is gonna be just f0 of p. Right now, as for qi of p, we can say that it's gonna be the probability of qi minus 1 of p, or fi of p. So qi minus 1 of p plus fi of p minus the probability of them happening at the same time. Alright, we have gotten ourselves the recursively defined, not really the solution. However, if we were to take the inverse function of this, then it is in fact gonna be our solution. Gonna have q, next we're gonna have almost 1, so 1. However, we're looking for a general solution n, as we have replaced that, so qn, the inverse of it, we fill in 1/2, and this is a solution. However, we still have to show that qi is injective, because otherwise the inverse is not going to exist. Well, injective at least on the domain that we're working with, which is probability rated, so from 0 to 1. Well, if we were to look into this, if we were to take the derivative with respect to p of this, we're gonna get a positive derivative on that range. Next, if we were to look into this, then essentially what we will get is we will get something like this. Wait a second. Qi prime of p is gonna be qi minus 1 of p, don't forget the prime, plus f of I p, don't forget the prime, plus qi minus 1 prime of p times fip. Okay, I forgot the minus sign. So minus qi minus 1 of p times fi prime of p. Next, we were to factor it. We're comping this and this, this and this. We're getting the derivative times 1 minus one of those functions, be it qi minus 1 of p or fi of p, right? And well, those are probability rated functions, so obviously the range is going to be from 0 to 1, so that can be negative. As for the derivatives, qi minus 1, q0 is has positive derivative, as we were already shown. Now qi of p is going to have a positive derivative as long as all I of p derivatives are going to be positive. Alright, I made a cut because showing that the derivative is positive for f of I is really annoying. Now, it's mostly just basic calculus. It's nothing out of the ordinary. However, it is a huge pain in the ass. I will probably make a link to some explanation in the description if you still want to see it. Alright, so at the end, assuming that f of I is gonna be injective too, well, not really injective, writing specifically here, then qi of p is going to be injective, so you can have an inverse of it. And the solution for the initially proposed problem, q of 1 over 2, this is the inverse, is going to be, again, we were asked about 10 decimal places, 0, 5, 2, 4, 2, 4, 3, 5, 0, 2, 9. Alright, that's it for today. Bye.